We have seen the solution of one-dimensional wave equation in Cartesian coordinate in previous lecture. And now today we are going to see the solution of the two-dimensional wave equation again in Cartesian coordinates. In fact, as we have seen in the earlier lecture, that we have solved the one-dimensional wave equation by taking an example of a string fixed at its two ends rigidly. Similarly, in this problem, we will consider the solution of two-dimensional wave equation in context of vibration of a rectangular membrane. So taking this example of vibration, or you may say transverse vibration of a rectangular membrane, we will solve actually the two-dimensional wave equation in Cartesian coordinates. As you know, in Cartesian coordinate, the two-dimensional wave equation is given in this manner. This is del 2 psi by del x square plus del 2 psi by del y square equal to 1 over v square del 2 psi by del t square. Here you can see that this wave function psi is actually a function of three independent variables, and these are x, y, and t. X, y are space coordinates and t is time. As I have told you that we will solve this two-dimensional wave equation in context of the transverse vibration of a stretched rectangular membrane. So for this purpose, let us consider there is a thin rectangular membrane and it is homogeneous. It means mass per unit area of this membrane is constant. And I have shown in this figure that this OABC is this rectangular membrane, and it is in xy plane, as you can see in this figure. And the length, that is OA or BC of this membrane, is A, and its breadth is B. It means OC is equal to AB, and that is equal to B. Actually, this membrane is stretched at all its boundaries. So you can see, since the boundaries are fixed, so they will any point on these boundaries will never get displaced. So now let us consider a very small element of this membrane. I have shown in this figure here, and this small element is at a point whose coordinates are x and y. When this membrane is disturbed, or you can say that a transverse vibration is set up in it, then actually a two-dimensional wave proceeds on this membrane. And the wave equation for that two-dimensional wave will be same as I have defined in this equation 1. So in context of this transverse vibration of membrane, our aim is to solve this equation which is defined in this equation 1. Actually, for solving this equation, there will be some boundary conditions, and you can see what are the appropriate boundary conditions for the solution of this problem. You can see the first condition is psi of x, y, t is equal to 0 on the boundary of the membrane for all t greater or equal to 0. As I have told you earlier that our membrane is rigidly fixed at its boundary, so any segment of the membrane will be never get displaced, and since in this case this wave function psi represents the displacement of an element of the membrane, so this displacement is 0 at all points on the boundary and at all time. So whenever x will run from 0 to A and y will run from 0 to B, this psi will remain 0. It means displacement will be 0. So this is the first boundary condition. Again, the initial displacement when you say psi of x, y 0, it means t is 0 and t0 means initial moment. So at initial moment, the displacement function psi will be only a function of x and y. It is obvious since you are taking the time t equal to 0 fixed. So definitely the initial displacement psi of xy 0 will be only a function of x and y. So I have denoted that psi of xy 0 is equal to f of xy. Similarly, the another boundary condition will be what? That the initial velocity of any element of this membrane, which is defined as del psi by del t at t equal to 0, because psi is displacement, so its partial derivative with respect to time t will be velocity, and when you take the limiting condition t equal to 0, it means you are talking about the initial velocity. So initial velocity will be also a function of x and y. So I have written here del psi by del t at t equal to 0 is equal to g of xy. Because t is again fixed, so this velocity, that is velocity at t equal to 0, will be only a function of x and y. Again, as you know that the motion of this membrane is considered in fact very small displacement. In fact, the displacement suffered by any element of this membrane is very small in compared to the dimension of the membrane. So this fact can be mathematically represented as that the modulus of the displacement at any time t, that is mod of psi xy t, should be less than m. And what is this m? Actually m is a fixed number, and this condition actually represents that motion is bounded. It means any segment or any element of this membrane will suffer a very small displacement which will have a finite value. It is never infinity. So this is the fourth boundary condition. So applying these four boundary conditions, you will see that solution of the two-dimensional wave equation, which I have defined earlier in this equation 1, can be solved. So now let us proceed how we can solve this problem. But before that, I am mentioning a very important fact. What is this v here? As you know, in this wave equation, this v is the phase velocity of the wave. And in fact, in case of the stressed membrane, this phase velocity of wave is equal to a square root of t over sigma. And here this t represents the tension per unit length. It means this is tension divided by length. And sigma is mass per unit area, or you may call it surface mass density. And in fact, these two quantities are constant in this case, as our membrane is homogeneous, so sigma will be constant, and we apply a constant tension too. So in this condition, these t and sigma are constant, and if t and sigma are constant, you can see that this velocity v, which is the phase velocity of the wave generated on this membrane, is constant. Now our aim is to solve the two-dimensional wave equation, which I have defined here. You can see in this equation 1. As you can see that this function psi is a function of three independent variables, that is x, y, and t. So, and at the same time, you can see that the equation is a second order partial differential equation, and you know the partial differential equation can be solved by adopting a particular method which is called variable separation method. Actually, after applying the variable separation method, our partial differential equation is splitted into the ordinary differential equation, and then we can write the solution of those ordinary differential equation. So for solving this equation, we will adopt the method of variable separation. And how this method is applied, you have learnt already in the previous lecture. So you can say we apply the method of variable separation to the wave equation, which has been defined as you can see in equation 1, and assume, as you have seen, that the displacement or the wave function psi was a function of 3 independent variables x, y, and t. So you can write the solution psi of x, y, t equal to h of x times w of y times g of t. Here h is only a function of x, w is only a function of y, and this capital G is only a function of t. In fact, if we separate this in a space and time part, you can see this h of x and w of y both represent the space part. So this product h and w can be written as a function f of x and y times g of t. So you can write this solution psi of x, y, t equal to this much. Say this is equation 3. Now, after writing this solution, you can use this value of psi in the given wave equation. So I am again writing here the given wave equation, and then we will substitute the value of psi which we have defined in this equation 3. So let us write the wave equation again. Now you can see our wave equation is del 2 psi by del x square plus del 2 psi by del y square, and this is equal to 1 over v square del 2 psi by del t square. Now we will substitute the value of psi from this equation 3, and you can see this psi is equal to f times g. So at the place of psi we will substitute f times g. So this will be del 2 del x square, and instead of psi we will write f times g plus again del 2 by del y square f times g, and this equal to 1 over v square del 2 by del t square f times g. Now as you can see that this f is a function of x and y, and g is a function of t, and we are here differentiating partially with respect to x. So this g will be treated as a constant, and so our result will be g del 2f by del x square, and plus similarly here g is a function of t, so it will be outside of the differential operator, and this is del 2f by del y square, and this is equal to, now you see the RHS. Here we are differentiating partially with respect to t, so f will be treated as a constant because f is a function of x and y, not of t. So let us take this f outside of the differential operator. So this is f over v square del 2g by del t square. Now you can take this capital G as a common factor in LHS. So this is g times del 2f by del x square plus del 2f by del y square, and this is equal to f over v square del 2g by del t square. Now you can see in LHS and RHS, both the functions of a space coordinate x and y and time t are present. So variables are not separated. To separate the variables, we will make here a simple algebra. In fact, for this, we will divide this equation, both sides, by the factor f times g. So to separate the variables, let us divide the above equation. Let us divide the above equation by f times g. You can see when you will divide this equation by fg, here g will cancel out and in denominator there will remain f, and here f will cancel out and in denominator there will remain g. So what will be your result? You can easily see here. So therefore our result will be 1 over f del 2f by del x square plus del 2f by del y square, and this will be equal to 1 over v square times g, and d2g by dt square. You can see here. By dividing this f of g, this g will cancel, so here remains f, and in RHS there will be g. So this is our equation. One thing you may note here, that in LHS I have written the partial derivative, that is we have used the symbol del x for differentiation. But in RHS I have used the ordinary differentiation operator, that is d dt. Why? Because you can see f is a function of two variables, x and y. So when you differentiate with respect to x, you take y constant, and when you differentiate f with respect to y, you take x constant. So in this LHS, I have not used the ordinary differentiation, but since g is only a function of t, it is a function of only one variable, so here there will be no difference between the ordinary differentiation and the partial differentiation. So I have used the symbol d2 dt square instead of del 2 del t square. So this is equation number what? You can see actually that will be equation number 4. So let us say this is equation 4. Now you can see variables are separated. This LHS is a function of x and y only, and this RHS is a function of t only. So you can see LHS is a function of x and y only, and RHS is a function of t only. RHS is a function of t only. You can see here. Now, since x, y and t are independent variables, so for all values of x, y and t, this equation 4 will be satisfied only when both sides of this equation will be equal to the same constant. You know it. So, both sides of equation 4 must be equal to the same constant. And in the solution of one-dimensional wave equation, you have seen that we have considered actually 3 values of the separation constant. And those 3 values were, first was actually 0, second was positive, and third was negative. But you have seen that the 0 value of separation constant and the positive value of separation constant do not give the solution of the wave equation. Actually, only when we consider the separation constant negative, only then our solution is actually consistent with the proper boundary condition. So here I am not considering all these 3 possibilities. I am directly considering that the separation constant will be negative. So you can say this constant should also be negative, which gives solution with proper boundary conditions. So I will write this constant directly, a negative constant, not positive, not 0, because 0 and positive value do not give the proper solution of the wave equation. So you may write, so let us consider that the LHS 1 over f del 2f by del x square plus del 2f by del y square is equal to minus p square. Actually, this minus p square is a constant. You can see I have taken p square because p square will be always positive. So due to this minus sign, this constant will be always negative. And so from here we can write that our equation will be del 2f by del x square plus del 2f by del y square, and this is equal to minus p square f. And equivalently, you may write this equation in this manner. This implies del 2f by del x square plus del 2f by del y square plus p square f equal to 0. So this is the equation in terms of the function of space coordinates. You know that this f is actually a function of a space coordinate x and y. So we have calculated, or we have found the differential equation which contains only a function of space coordinates. Now again, you can write the RHS of the equation equal to the same constant. So you can see in RHS of this equation there is 1 over v square g d2g by dt square, and that should also be equal to minus p square. So again you can write 1 over v square times g d2g by dt square. This is equal to minus p square, and from here you can see this d2g by dt square plus v square p square g is equal to 0. So this is another equation which contains the function of time t only. This is an ordinary equation. Now we will solve the equation A and equation B separately. So solution of f equation, solution of f xy equation. Separately we will solve equation A and equation B, and after that we will get the complete solution of the wave equation. Now you can see this equation A is actually a partial differential equation. So again we will make the use of variable separation method to solve this equation. So as equation A is a partial differential equation of second order. So we apply again variable separation method. Variable separation method. You can see that f is actually a function of two independent variables. One is x and another is y. So this equation will be again splitted into two ordinary differential equations, and for that we will write the solution of this equation A in this form. So let f of xy is equal to, as I have written in fact earlier, this is equal to h of x into w of y. Actually I have mentioned this product earlier. You can see in the beginning I have considered it. This is h of x times w of y equal to f of xy. I have already considered it. So now this value of f will be substituted in the differential equation defined in equation A. So let us make the use of this equation. Let us say this is in fact equation number what? This will be equation number 5. So let us say this is equation 5, and we will make the use of equation 5 in equation A. So using 5 in A, we get, as you can see, your equation is what? Your equation is del, you can see here, our equation is this much. So del 2f by del x square. So this is del 2 by del x square f, and f is equal to h times w, plus del 2 by del y square hw, and plus p square f. So this is not equal to but plus p square f. F is equal to h times w, and this equal to 0. This equal to 0. So now you can see h is a function of x, and so it will be differentiated, and w is a function of y, so it will be outside of the operator. So this is w del. Now instead of del you may write d, because this h is only a function of x, so there will be no difference between the partial derivative and the ordinary derivative. So we can write this is d2h by dx square, d2h by dx square, and plus here differentiation is with respect to y, so w will be differentiated and h will be outside of the operator. So h d2w by dy square, and plus p square hw equal to 0. P square hw equal to 0. Now again you can see that variables are not separated. So to separate the variables, we will divide this equation by this product hw. So to separate the variables, let us divide the above equation by h times w. What we will get? You can see here this w will be cancelled out and h will remain. So this is 1 over h d2h over dx square, plus in this second term h will cancel out, and in denominator there will be w. So this is 1 over w d2w by dy square, and plus here this hw will cancel out, so this is plus p square, and that is equal to 0. Now let us simplify this equation to some extent. So you can see from here that this 1 over h d2h by dx square is equal to minus, you can see, let us take these two terms in RHS. So this will be minus 1 over W d2W by dy square and minus p square. And you may write this equation in this manner. This is 1 over h d2h by dx square, and this is equal to minus 1 over w. We take this minus 1 over w as a common factor, and when you will take this as a common factor, what will be your remaining terms? This will be d2w by dy square plus p square w plus p square w. And now you can see that let us say this is equation C. Now you can see this LHS of this equation is a function of x only, and this RHS is a function of y only. And as you know, x and y are independent variables. So for all values of x and y, this equation will get satisfied only when both sides of this equation will be equal to the same constant, which is called actually separation constant. So you can write, I am not writing this argument, you can understand it, what I am telling you. So you can write 1 over h d2h by dx square, and this is equal to a negative constant. Why negative constant? You have already learnt it, that when we consider this separation constant 0 or positive, we do not get the proper solution of the wave equation. Only the negative constant, negative separation constant gives the solution of wave equation with proper boundary conditions. So I have considered here a negative constant that is equal to minus q square. So this is a negative constant, and so you can see this equation may be written as d2h by dx square plus q square h is equal to 0, and say this is equation D. So this is an equation in terms of h. Now again the RHS of this equation C will be also equal to the same constant minus q square, as you know. So again you can say that this minus 1 over w d2w by dy square plus p square w, and this is equal to minus q square. Now let us simplify this equation to some extent, and so you can see that this d2w by dy square plus p square w is equal to minus q square w. Now take this term in RHS to LHS. So bringing this in LHS, what will be our result? This is d2w by dy square plus you can see p square plus q square w, and this will be equal to 0. P square plus here I have done a mistake. because here is minus sign, so this minus minus will cancel out, and so here will be plus actually. And if it is plus, then at this point you can see there will be minus sign. So this is p square minus q square w. Now let us consider that this p square minus q square is equal to r square. Let us consider it. So you may write d2w by dy square and d2w by dy square plus r square w is equal to 0, and say this is equation E. This is equation E. And you can see this is the ordinary differential equation of second order with constant coefficient in terms of a function w, which is a function of only one variable, that is y. So this is an ordinary second order differential equation. So here actually I have written that this r square is equal to p square minus q square. Now you have two standard second order differential equation. You can see in equation D we have a second order differential equation with a constant coefficient in terms of the function h, and in E there is a second order ordinary differential equation with constant coefficient in terms of the function w. And as you can see, both of these equations are actually the equation of simple harmonic motion or simple harmonic vibration, and so definitely their solution will be oscillatory. And when you say that solution is oscillatory, it means you can write the solution as a combination of sine function and the cosine function. So now you can directly write their solutions. Now solution of equations D and E are given as, you can see our equation D is this much, and you can write the solution of this equation as h of x equal to an arbitrary constant, let us say a cos qx. See here, this will be a cos qx plus b sin qx. You know it. And similarly, the solution of this equation E will be what? This is w of y equal to an arbitrary constant, let us say c cos ry plus d sin ry. So let us say this is equation F. Here actually A, B, C and D are arbitrary constant. Actually these are integration constants, and you know we evaluate these arbitrary constant by using the proper boundary condition which I have mentioned earlier. But as this problem is slightly longer, so I will divide this problem to just like the one-dimensional wave equation in two parts. So I am ending my lecture at this stage in today, because if we will complete the problem, there will be a lot of this will take a longer time, and that will be not very convenient to you. So I am just ending my lecture at this stage, and in the just second lecture we will discuss the complete solution after this step. So I will suggest you, whenever you will watch the second video after this, definitely you have an idea of this first video, and so definitely you watch this, and just in successive manner you should watch the second video. So I am just ending my lecture at this point.